In this video, I'm going to go through the process of calculating a confidence interval for a population mean. And as I often do, I'm going to make two passes through the problem. The first time through, I'm mostly just going to solve the problem and I'm going to leave out a lot of details. I'm not going to necessarily address how things would be different if the situation were slightly different. Then I'll come back and I'll go through it again, remind you of what I did, and add some more details. So I think the first pass through will be useful for everyone. The second pass through will be mostly useful for people who are seeing this for the first time or really not super comfortable with this yet. All right, so in front of us we have a problem, and I'm just going to read through the prompt. A pharmaceutical company is testing a new drug that is intended to lower cholesterol in adult men. They test the drug on a group of 15 volunteers and have everyone in the study take the drug for 2 months. They measure cholesterol levels before and after the 2-month period and record how much each subject's cholesterol level dropped by. The following values are the 15 changes in cholesterol measured in the study. So we have this list of numbers, and then we're told that these values are in milligrams per deciliter, and a positive value means that the subject's cholesterol level dropped. So a negative value would mean that their cholesterol level actually went up while they were taking the drug. Estimate the average drop in cholesterol for an adult male who takes the drug for 2 months. All right, so step 0, which really isn't actually part of finding a confidence interval, it's just part of answering any statistical question. It's before you know what you're supposed to do. We aren't told to calculate a confidence interval here, so why should we calculate a confidence interval? We are trying to estimate, so it's a numerical question, the answers should be a number, an average for one quantitative variable that describes our population. So we are estimating a population mean and when we're estimating, we need to calculate a confidence interval. Now, our steps for a confidence interval are just like those for a hypothesis test, but we don't have hypotheses. We actually start with conditions. So step 1 is conditions. And our conditions are the same as they were for a t-test for a population mean. So our first condition is randomization. And I'll go back up to the prompt. What's being described here is an experiment. It's that they're administering the drug to people, and it's a group of volunteers. So we don't have a random sample, which we don't expect for an experiment, but there's also not a control. Everyone in the study is taking the drug for 2 months. So this is an unrandomized experiment. So the condition is not satisfied. And this will sometimes happen. It doesn't stop us from doing the whole problem. We'll address it in the conclusion. So I'm going to put a red X next to this, just reminding myself that condition was not satisfied. For the independence condition, I always start this condition by just stating what the population is. So we're studying how this drug works in adult men, so that's our population. And the condition for independence is that the population is at least 10 times the size of the sample. We have a small sample. The sample size is 15. So this population is certainly 10 times the sample. That is to say, there are more than 150 adult men. So independence is satisfied. So let's, I guess I should make a little mark next to this as well. Put a green check mark. Okay, that one was satisfied. And then our final condition is the condition on data. And we first identify where our sample size falls. Our sample size is less than 16. And so our sample is small. And to check this condition, we need to check that, in fact, we have a roughly symmetric distribution with no outliers. So I'm going to enter this into RStudio. Luckily, I have this as a comma-separated list. I think I do. So I can just copy it in. I'm going to call it COL for cholesterol. Oops, something happened there. Let's just check whether this got entered. Yeah, anytime you get an error message, you should confirm that your data set entered right. And it did. I'm not really sure why that happened. This has happened a few times. So we have our data set entered, and now we're going to have to check a histogram and a box plot. And all right, I'm getting an error because I'm zoomed in, but I don't think that's an issue. Let's see what happens. I think I can still look at this. Maybe I can't. So let's zoom back out first. So it'll this always happens when I'm zoomed in on the code, that it's hard to see. I'll type the same thing. So I'm going to do a histogram and a box plot. And then let's see, hopefully we can see these kind of well. Yeah, that's not exactly right. There we go. All right. So there we have a box plot. And there we have the histogram. So looking at these, the box plot was fine, right? The box plot, we're checking whether there are outliers. There's none. There are no dots on the edges. For the histogram, staring at this, you might say, is this, I don't know, maybe this is a little right skewed, but remind yourself, this is a data set of size 15, right? This is a very small data set. And if I moved a single value, all of a sudden it would look symmetric. I'm going to call this roughly symmetric. I don't see any skew that's obvious enough to justify calling this skewed. So I'm going to say that this is roughly symmetric. So let's go back to this view. That was not what I wanted to go to. There we go. Let's zoom back in so we can actually see this kind of well. There we go. All right. So I decided that the histogram is roughly symmetric. And there are no outliers. That was from the box plot. And the reason that this is what I was looking for, that this is what I was checking, was that this is a small sample size. Our sample size is less than 16, it's 15. So this is satisfied. So 2 of our conditions are satisfied, 1 isn't. We'll come back and address that when we write our conclusion at the end of the problem. All right, so step 2 is calculations. And in my calculations, what I'm going to want to do is I'm going to have to use software to calculate really just a small amount of stuff for this data set, and then put that all together to get a confidence interval. So I want to identify the pieces of information I need. The formula for a confidence interval, it can be useful to write this down kind of as early as possible, because it just reminds you of all the things that you need. And right now I know one of these things. N is 15, that's the sample size. And so let's get a few of those other things. So I can get the mean value. I don't know why it keeps doing this. I think it's maybe when I switch zooms to zoom in on the data that it does that. So I get a value of x bar equals 24.04. Get a value of S of 18.803. That's my standard deviation. And the final thing I need is T star. And I think T star is the trickiest part of this, but luckily in the end, there's a very formulaic way of calculating it. And in particular in this problem, I don't even have enough information to calculate T star. So here I decided I needed to calculate a confidence interval, but it turns out the problem just told me to estimate, and it didn't specifically say to calculate a confidence interval. A lot of the time, or almost all the time, we'll just tell you what confidence interval to calculate. We'll say, hey, calculate an 80% confidence interval or something like that. But sometimes we don't. And in particular, one of the harder tasks in this course is identifying which procedure is right. And if I tell you to calculate a confidence interval, you know you're supposed to calculate a confidence interval. But we don't need to be told to calculate a confidence interval to know that this problem requires a confidence interval, right? It's a confidence interval because we are estimating the population mean. Long way of saying, it didn't tell us what to do. I'm going to choose to calculate a 90% confidence interval. All right, so the place that the 90% comes in is in calculating T star, right? So far, everything I've done does not rely on the confidence level. So T star I like to write it like this. So it's a QT. So this Q for quantile. And I write it like this, 1 plus CL over 2 dF. What do I mean by this? dF is just the degrees of freedom, in this case 14, right? It's still n minus 1. And 1 plus CL over 2, well, I'll write out what it is. It's 0.95, and then I'll show you how I got that and what that symbol means. So this is what I need to type into RStudio. So let's quickly get that out of the way. I got 1.761. And what is this 1 plus CL over 2? CL just refers to the confidence level as a decimal. So if it's a 90% confidence interval, when I turn 90% into a proportion, a decimal, I get 0.9. And when I add 1 plus 0.9 over 2, I get 0.95. I'll explain in my second pass through why this is what you should do. But if you're just looking at how to calculate it, this is the rule for calculating these confidence intervals. All right, so I need another page here. And oh, I forget that it always does this. Let's add a page that doesn't have. Let's just add a blank page. And it ends up looking a bit weird, but that's fine. So we need this extra page. All right. Yeah, so we've got an extra page here. So let's finish this up on this next little page. So our confidence interval is x bar plus or minus T star times S over the square root of n. And I can plug in all those numbers now. I calculated x bar. That was 24.04. I calculated T star. That's 1.761. I calculated S, 18.803. And N was 15. And I get two numbers out of this. So on one hand I add, on the other hand I subtract. And I like to do this all at once in RStudio, and I'll show you what I mean. So I'm going to do the minus part first. And the reason for that is that that's the thing that goes on the left, the smaller number. So 24.04, I'm going to do the minus part. 1.761 times, remember I need to always write in an asterisk when I'm multiplying. And then divided by the square root of 15. Click enter, and that gives me my lower bound. You could also have calculated this piece by piece, right? The reason I like to type it in all at once is that it doesn't, or it allows me to not worry about rounding, right? I've already made some rounding decisions, but, and I'm going to round this to just one decimal place. So I'm going to say this is 15.5. That's our left side. And the nice thing when you work in RStudio is you can just copy paste, right? Because the only difference to get the right side is instead of subtracting, I have to add. So once you've clicked enter, you can't edit something. You can copy it, paste it to a new line, and change it. And now I click enter and I get the upper bound, which is 32.6. So that's my whole calculation. So I have my confidence interval. Now let's zoom out since we're just on this page. And so now I get into step 3, which is where I write my conclusion. And my conclusion for a confidence interval is really, conclusion is not maybe the right way to state it. It's more of an interpretation. This confidence interval is just a set of numbers. I want to take us back to the actual problem and say, what do these numbers mean in the context of the problem? Remember, our goal here was to estimate the average drop in cholesterol for an adult male. So these numbers are telling us what our estimate for the average drop in cholesterol for an adult male is. So when I put that into a sentence, I'll say something like this. We are 90% confident that and these can be trickier to write than it may initially seem. We are 90% confident that adult men who take the drug for 2 months, so I want to include all of the context that I have, will have an average drop of blood pressure of between, and this is where the numbers come in. And remember, the units were milligrams per deciliter, and it doesn't really matter if you don't know what that means. I don't really know what it means. I mean, I know what milligrams and deciliters are, but I don't know all that much about cholesterol. So are between 15.5 milligrams per deciliter and 32.6 milligrams per deciliter. So again, we are 90% confident that adult men who take the drug for 2 months will have an average drop in blood pressure of between 15.5 milligrams per deciliter and 32.6 milligrams per deciliter. It's hard to write these sentences, and in certain contexts it can be even trickier. But one thing I'd recommend is when you write a conclusion, read it back over. I think this conclusion is reasonable to me. That is, the words make sense. Sometimes you'll write something, I'll do this, and I'll read it back and say, well, that is not a good sentence. And then you want to go back and edit it. But I'm not done here. So this would be fine if my conditions were all satisfied. We haven't seen this yet, and this applies to a hypothesis test as well. When a condition's not satisfied, you need to mention that in your conclusion interpretation section and say something about what it means. So when randomization isn't satisfied, the issue there is that we have results that apply to a non-random sample that was not in a randomized experiment, but we don't really know that this should generalize to the population. And so I'm going to say something like this. Since the results are from an unrandomized experiment, they may not generalize to the population. I'll say it like this to emphasize, to the whole population. Of adult men, right? Maybe it's the case that the people who volunteered to participate in this experiment were also watching their diet, and that was actually the reason that the cholesterol dropped, right? So we state our conclusion. This is kind of the confidence interval part, this top portion. That's what we would always do. But anytime one or more conditions isn't satisfied, we include that in our conclusion. We mention, at least briefly, how that might affect our results. All right, so that was my first pass through. And I know that took a while, but hopefully if you were having issues calculating confidence intervals, or if you just hadn't seen this at all before, that was somewhat useful. My pass through is going to be a bit shorter than it was for hypothesis testing, because actually a lot of things I can just pretty quickly skip over because they're the same. So let's go back to the beginning. All right, so step 0 is something that slowly becomes more and more important as the course moves on. Just each time we have a new procedure, it becomes harder and harder to decide which procedure should we do. And so even though the title of the video says confidence interval in it, remember this prompt did not say confidence interval in it. The reason that we're calculating a confidence interval is not because I told you to, or because the video has that in its title. It's because it is the appropriate thing to solve this question that we're trying to solve. And that's what step 0 is all about. Identify what to do. It's a confidence interval because we're estimating. Anytime we're estimating something, that's something we do with a confidence interval. And the reason it's this specific one, which is the only one we've seen so far, is because what we're trying to estimate is a single population mean. All right, conditions. I'm going to skip through this because the conditions for the T confidence interval are exactly the same as the conditions for the T hypothesis test. There's no difference between them. And so if you need to brush up on those, go back to the video I made about calculating the one sample t-test for a population mean and skip to that part where I talk about the conditions. We always have randomization, which is random sample or randomized experiment, independence, populations 10 times sample, and our condition on data depends on sample size. In this case, we had a small sample size, less than 16, so what we needed to check was roughly symmetric and no outliers. All right, calculations. The calculations for a confidence interval, I think, are relatively straightforward, except for the whole T-star stuff. That is, T-star to me is the biggest tripping point. Anything else that you find tricky, I think with practice, which you'll get a ton of, you'll figure out. So let's talk about T-star, and let's flip over to a different sheet of paper so that we have space. So calculating T-star. And so I just gave you a formula for it, and I want to start from the picture because the picture will explain why it works the way it does. So the whole idea is that in this problem, we wanted a 90% confidence interval. So we want the middle 90% of values. The total area is 1, and so the middle 90% is 0.9. Now the value in the middle is 0. And so that means that for the middle 0.9, due to the symmetry of the t-distribution, we'll have a positive value over here, which is what we're calling T-star, and then the negative of it, minus T-star. So we want the value that encompasses the middle 90%. And if you keep drawing, or not drawing really, but if you keep labeling areas, you realize that these two outside areas each have to be 0.05. We have symmetry, so they have to be the same area, but they have to add up to 1. And then when you look at this, you realize that the area to the left of T star is 0.9. That's this first part, plus 0.05. Or in other words, T star is the 95th percentile. And I should write up here, just to remind us, this is for a 90% confidence interval. And so right off the bat, we see, oh, T star, even though it's a 90% confidence interval, it's not the 90th percentile because we're referring to the middle 90%. And percentiles always are referring to how much is less than something, how much is to the left of it. And so what this ends up meaning is that if it's the 95th percentile, the command to find it is QT of 0.95. And 14 because the sample size was 15. So that was how I calculated T star. And this picture explains why it's not actually just 0.9 in there, right? It's 0.95. So do you have to draw the picture each time? Absolutely not. In my mind, there are two ways to look at this. Or sorry, maybe three. One of them is just to draw the picture each time, and that's totally fine. Drawing pictures is great. But if you want like a quicker approach, the first thing I'd say is the most important thing is just to remember that it's not 0.9 for a 90% confidence interval. And this may seem like a weird thing to say, but my point is that if every time you calculate a t-star value, the only thing that you actually remember is that the number you're plugging in is not just the confidence level, then you'll be fine because you'll go look it up. The biggest mistake I see people making is they go on autopilot and they just think this number is whatever the confidence level is. And as long as you're constantly reminding yourself, nope, it's not the confidence level, you can just go look it up. All right, so what is it exactly though? It's what I write as 1 plus CL over 2. So in this case, and by CL I mean the confidence level is a decimal, I get 0.95. What we're really doing here is we're averaging 1 and the confidence level. The idea being that we don't actually want the 90th percentile, we want to move it up a little bit. So the calculation is always 1 plus CL over 2. And so your formula is T star equals QT of 1 plus CL over 2, and then the degrees of freedom. Again, this confidence level is as a decimal. And so if you just remember that it's not just the confidence level, like I said, I think that's most of the battle, and then you can go look it up. But eventually, if you practice it enough, you'll get to the point where this is relatively straightforward. And again, you can draw the picture, you'll get the same thing. If you really want to be careful, you can do both. Draw the picture, see what you think makes sense with the picture, and then also plug it into the formula. So flipping back, T star was the only thing that was kind of a new calculation. And then when we computed this confidence interval, as I said, you can do it piece by piece, right? You could do this division first and then multiply it out and then add and subtract. But typing it all in at once has two advantages. It avoids rounding. And as I showed, the first time you do it, you subtract to get the left number. The second time you do it, you can just copy and paste and change the minus to a plus. So that gave me this interval. All right, finally, in the conclusion/interpretation, the whole idea of a confidence interval is that we don't want to just give our estimate, right? So here X bar was 24.04, and we could just say, people who take this drug for 2 months, their cholesterol drops by about 24 milligrams per deciliter on average. However, we know that number is probably not exactly right because it's a sample estimating a population, but also we don't, in that sentence, express how far off we think that number should be. And so the whole idea of a confidence interval is we are doing that. We're saying, hey, how far off do we think our estimate might be? And so when we say we're 90% confident, what we're saying is that we've created this interval, 15.5 to 32.6, and this whole process, 90% of the time, produces an interval containing the correct value. So that is if this company produces lots of different drugs, right, and they're testing all their different drugs, and they're always reporting 90% confidence intervals for their effectiveness, 90% of the time, the interval they report contains the true value, 10% of the time it doesn't. And so we say something like this: we are 90% confident that, so that's how we always start, just, we are some percent confident that something. And then the second part of the sentence is saying, what is our interval telling us? And it's always, this interval is an estimate for the average drop. So we're 90% confident that adult men who take the drug for 2 months will have an average drop in, I said blood pressure, didn't I? I think I was doing a blood pressure example earlier. It's very easy to make these sort of mistakes when you're doing too many things at once. It's an average drop in cholesterol levels of between 15.5 milligrams per deciliter and 32.6 milligrams per deciliter. That's as I said, our kind of standard sentence. And these will get trickier in different contexts, but even now it can be a bit tough to write. And then finally, we have to address the fact that we didn't satisfy all of our conditions. We have an unrandomized experiment. And when you don't have randomization satisfied, your big concern is that your results may not generalize to the entire population, right? If you had a non-random sample in an observational study, or when you have an unrandomized experiment, you do have to wonder this. As I said earlier, in this case, you can kind of see why. That is that volunteers who agree to participate in a cholesterol study likely are doing other things to try to lower their cholesterol. And if we had a control group, we'd be able to compare how well the drug did versus versus nothing, and take that into account, that people might be exercising or changing their diets. Here, this result doesn't do that, and so we can't really be certain that this actually generalizes to the whole population. All right, so again, with these long videos, thank you if you stayed this whole time. I know it's a bit long. Hopefully that was helpful, and hopefully it cleared any confusion up that you have on how to calculate confidence intervals for population means.